And I think with that, I cover all the functionality and steps for MEBS. And now we can get to the basic usage in the GitHub. Okay, one important thing to consider, MEBS was originally described in this other repo that it's not currently maintained. However, everything in that repo, if you run MEBS, should work, but it's not currently updated. So that's one thing to consider. And then another important thing is that we try to keep track of all the changes that we do. And here we are putting kind of the main changes, the scripts that we have, and everything it's in there. Examples of papers that have used MEBS in here. Right now, I got a notification that MEBS was incorporated into this review about metagenomics, and I was very excited about that. And another important thing to consider, so if you look at the at this workshop when you come back and you have some issues or questions or something is not working, please use the issues section. In this way, I can keep track of everything. There are sometimes questions that somebody else has, and it's already in there. So please, I encourage you to use this issues section in the GitHub. This is the citation. And one thing to consider are the versions. So the first version of MEBS, which was described in this original PDF, was before we had a single script. Before incorporating all the changes, I used to compute the scores with 2 scripts. Now we incorporate that into one. But that was the original way in which we used to compute MEBS with 2 different scripts, one for genomes and one for metagenomes. And that was the first version that was released originally. Then the second version was released 1 year later. And this is the manual in which we incorporate now the main script and to plot the results and all the things that I show you. But that was the previous version, and now this version 1.2 has incorporated the marker genes, and it has incorporated how you can do the PFAM clustering. And the previous versions, the PFAM clustering script was not there. In this new version, we have the PFAM clustering script, and we have the marker genes. So I encourage you to use the most updated version of MEBS. And I'm just going to go through the manual very quickly. I'm going to give you some advices, and I will encourage you to please give me some comments, and if something is not clear, and some recommendations you can do. I'm not going to have time to do it like command line. I try to put everything in there so you can go and follow it with me later. And so that's why I want to spend just a little bit of time to explain the manual. So here is the description of MEBS, the authors. I put the information, the webpage of each one of us. Here I try to put a very brief condensed version of everything that I explained about the relative entropy. And here I have the built-in functions that I already explained about the sulfur, carbon, nitrogen, and sulfur cycles. One thing to consider, though, is for carbon, the carbon score is using all the information of Keck about the methane cycle. So what we are screening actually is the methane cycle. All of the PFAMs and all of the genes involved in the PF and the Keck methane cycle are incorporated in there. So just to keep that in mind. The applications, that's something that you already saw. And so this is the part that I want to talk about. So the main components. MEBS has three main scripts that have been tested in Linux and Mac systems. The first one, it's, oh my God, here there's an error. The first one is written in Perl, and the second and the third one are written in Python. The first script is the one in which you're going to use to compute your scores and your pathway completeness and marker completeness. The second script is the one that you're going to use to visualize that output. It's going to give you a directory with outputs, and it's going to give you the information that you need in order to map that information if you have a tree in ITIL. And the third script is the one that you're going to use to compute the clustering analysis, the PFAM clustering of all the most recent PFAM database. If in the future there is a newer PFAM database, this is going to be updated. That doesn't mean that it's not useful. It means that we just need to incorporate a newer version of PFAM just to have it updated. So system requirements, what you need to have in your path, you just need to have Hammer search. And this is very easy to install and all of the flavors that you have here. So here I'm putting some options. If you want to have more information, you can go to the documentation of Hammer. But in theory, just by typing this, you can install Hammer easily. And then you can type, that's for the MEBS script, the main MEBS script. And then for the visualization, since many of the graphs are obtained with Python and Seaborn and Pandas, and we do some computing, some calculations with those scores, we use Python 3. So here I am putting some of the options on how you can install it. But if you don't have sudo permissions, then you have a Conda option. If you are more comfortable with Conda, we provide a MEBS environment that was done by JD, a grad student, which was amazing to have that incorporated in there, because sometimes it's the dependencies are broken and you cannot install all of this. So we provide this environment for you. So the way, and those are the only requirements that you would need. So you can test MEBS in your local computer if you have Linux or Mac system. And if you want to do it, you can follow me with this and try to download MEBS as we go. And then you have to CD into the directory. You have to be inside the MEBS directory. And here are some considerations. First, you have to have an input directory of Mac's metagenomes or genomes. And the type of data you just have to specify it. An important thing is that your genomes, metagenomes, or Macs have to have the extension FAA. If they don't have the FAA extension, MEBS is not going to recognize them as amino acid files. The header and the name of your files, that it doesn't matter. You can have the header that you want, the names that you want. As long as you have FAA, in theory, it should run. And then you just have to specify the type of data. So the first program, MEBS.pl, just have these options, as I was mentioning, the FASTA file directory, and the nature of your sequences. So you just have to specify genomic. You have to type genomic or metagenomic. Since I already pre-computed all the false discovery rates for all the cycles, you can be very kind of more restrictive in terms of how you want to score your scores, let's say it that way. If you want to only keep the ones that are significative, you choose a lower false discovery rate. If you want to be more relaxed, you choose a false discovery rate of 0.1. The one that it's by default is this one. So I encourage you, if you are analyzing Metagenome assembled genomes, I encourage you to use the default fault discovery rate, because in order to not get rid of things that could be potentially important. Then if you type cycles, you can see the currently cycles that we have. And the comp option is to compute the metabolic completeness. So one of the things that I got a lot of questions is that MEBS is not running, even though I have a FASTA directory and I am putting all the options. You have to consider that you have to be inside the MEBS directory. Why? Because when you run this, MEBS is gonna look for files that are in the config directory, and if you're not inside the MEBS directory, it's not gonna run. So that's one thing that you should keep in mind, and that's why I put in here to run MEBS. Make sure that you're inside the MEBS directory, and the type of data, you have to have the FAA extension, and Hammer Search must be previously installed. I know that it might sound repetitive, but yeah, I just wanted to make sure that it is clear. So an example input, if you don't have data yet and you want to test and you want to know whether MEBS works, you just have to type this command, perl -input, your test directory and the type of genomic data. So I have a directory containing 8 genomes that it's already in the GitHub repository, and you just have to type genomic. And then I also provide 2 metagenomes that are very tiny. And just to make sure that it works, just run these 2 commands, and you should get something like this. So the output, basically, if you just run MEBS without the comp option, you're gonna get the scores of your genomes, and with an asterisk, you're gonna have the ones that are significative for that cycle. So for example, for sulfur, we know that Archaeologus profundus is important for the sulfur cycle, and it has obviously a significative sulfur score. So that's pretty much it. It doesn't require you to do anything else. In terms of computational time, and that was something that we wanted to test, and that's something that I do want to emphasize. The first time you run MEBS, the first time you run this command, for each genome that you have in that directory, MEBS is going to compute the searches with Hammer Search and the databases that are provided. Once you have done this, you don't have to, next time you run MEBS, imagine that you have a directory with several genomes and you want to incorporate more genomes. You don't have to delete what MEBS already computed. You just put all the next genomes there. MEBS is going to check the files that are there. And if those files are already present, you don't have to worry about pre-computing those searches again. The searches are going to be there. The files are going to be there. MEBS is just going to check for those files, and it's going to compute the scores or the completeness of the genomes that you incorporate into that directory. And this is important to consider because that reduces the computational time. So the first time you run MEBS with this, with 8 genomes, it takes about 2 minutes, 1 minute. But the next time you run MEBS, since those searches are already pre-computed, it takes a few seconds. So that reduces the computational time. Now, the other option that you can use for the metabolic pathways is when you are using the -comp option. So the -comp option is going to give you a file that looks like this: sulfur, sulfur, nitrogen, nitrogen, markers, markers. And the information is the pathway completeness based on the prefams that are previously in the mapping file for each of the cycles. So let me just show you. So here we have MEBS. And if you go inside the cycles directory, for each of the cycles, we have a pfam to keg tab. Here, it's the mapping file that we are using in order to compute the metabolic completeness. So here are specific pathways or marker genes, and these are the pfams. And the file that you're gonna get here, the value that you're gonna get here is based on those pfams that are described in the mapping file for each cycle. So if you wanna be curious about this, for each genome, you're gonna have a file that ends with hammer search tab, which are all the searches, and then hammer search score. In that information, you have the pfams found in that genome, the specific entropy of those genomes, and the number of matching peptides. So here is the information of how many, or the counts of that pfam. If you want to know how many counts or how many times does that pfam appear. Since the score doesn't take into account the abundance, but rather the presence and the entropy, it's just the sum of that, and that's the pfam entropy score. That's the score that you're gonna see. So this is only if you want to look into the detail of the specific pfams found in that specific genome. If you have thousands of genomes, then you have to look at, and you don't want to look at this file, it doesn't matter. It's just if you wanna take a look into this. So now let's move into the MEBS visualization script. This script has several options. The only required option is the file that it's derived from MEBS. And you can customize your output. You can specify an output directory. You can specify the type of image that you want, the resolution of your figures, etc. And the way that you run it, it's just by running Python 3, the script, and the output from MEBS. Once this is running, you're going to have an output that looks like this, and it's going to have the description of all the files that were generated. If you don't specify, it says that you didn't specify. It's going to create a directory that it's going to be exactly the same as the name of your data set, and it's going to create all of these files. Here in the README, I describe each of the files, and I describe the figures. For example, these are the files that you're going to generate: 4 figures and 6 text files. The ones that have the scores, or that represent the scores, are this. For example, a dot plot, a bar plot, and a heat map. Here, for example, is the way that you can represent the scores if you have less than 100 genomes. If you have more than 100 genomes, then this is visually impossible. So there's a limit in which, for visualization purposes, but you're still gonna have the files. And this is important because if you use these files and you put these scores into the tree, here I just put the example of the iTool tree, in which you can have the scores in here, and also you can put the metabolic completeness, right? So you can put all of it. You can change your visualization in iTool, and those are the things that you can do with those scores. But as I was saying, yeah, those are the normalized scores that are provided in the text directory, and the normalized scores is what you are seeing here. And the same scores can be, as I was saying, plotted in iTool. So now the metabolic completeness. As I was mentioning, the -comp option. This is the mapping file that I show you. And this is the script that this is the heat map that you get also in the same output directory. For each of your genomes, you're gonna have the presence absence of a specific PFAM's completeness in this heat map visualization. So now the genomic completeness is what I was mentioning, and it's just the columns of the file derived from metabolic completeness, and you can plot those values, or you can use the specific values. Those values are there in the output. And finally, I put here the example of how to run the protein clustering. Here, it's important that you go to this MEBS PFAM release, since it incorporates the newer PFAM database. I had to put it in a release because there's a limit in what you can put in the GitHub repository. So you have to download these files from here. And then once you download the files, you can download them from here. You just have to take into consideration that it's almost 2 gigabytes, the size of this release. And you just have to take into consideration that when you screen each genome against the PFAM database, the files are going to be big. So that would be limited by the storage that you have and this type and the genomes that you have. In this case, we did use our servers in order to run it for thousands of genomes, because for each genome, you're doing a search against a database that is 2 gigabytes. But if you have less genomes, then you can potentially do it in your computer. So once you download the data, you uncompress the data, and it is important that you have to change the config file. In MEBS, there is a config file, cycles MEBS config file. In this config file, it is important to consider that every time the user wants to add a new pathway, it has to put the information here in order to MEBS recognize the path and run. Otherwise, it's not going to run. So if we want to run the MEBS clustering data, we have to add that here. And I already provide that information. So I already provide that config file that has already the line that you need in order to run it. So you don't have to worry about that. But just make sure that you do that first. So here I just put the command to put that into the config file, and now we go to the main path for MEBS. And now what we have to do is run MEBS again, because MEBS is going to do the searches. So here I am showing an example of how to do it with the input test minus comp, and here you're going to have a profile. So that profile is going to have all of the columns are going to be your PFAMs and all of your genomes. This is going to take a while. For example, half an hour for 8 minutes or 8 genomes. It's going to take more if you have more genomes, obviously, and the computational power. So now from this file, we're just going to extract the columns that we need. The columns are just the PFAM presence absence profile. And that is basically going to be the input for the clustering script. This is the clustering script. These are the specific options. And the only requirement for this script is that profile. As in the script above, we have some options that you can change: the resolution of your figures, the cutoff that you use, the method, the distance. You can customize that. But as a first approach, you can use the default options. So something important to consider is when you are analyzing presence absence, Jacquard distance is preferred. If you have abundances, and if you're not using this type of data, but still you want to use the script, I recommend right distances for the type of data. But yeah, so to run it, you just have to run Python, MEBS, cluster, and your profile. This is gonna generate, again, another directory in which you're gonna save your results in there, and it's gonna create a figure and several files. This is the figure that you're gonna generate by running this script, and this is basically the clusters and with the specific cutoff. The clusters are gonna be stored in the file. So for example, here I just have 8 genomes, right? But as I was mentioning, if we have several thousands of genomes and you don't know which genomes belong to that cluster, MEBS cluster script is gonna give you in that directory all of the genomes that belong to that cluster, and you're gonna know which cluster it is because they are divided by cluster. And yes, and it specify what type of the name of the folder directory. And that's it. That's pretty much it. Here are some of the papers, example papers that we have done with MEBS. This is the same. This is basically the same figure here, but instead of using 8 genomes, we have almost 2,000. And as you can see here, you can clearly see the differences between those clusters. You can map genes into a phylogenetic tree, and here I show other examples. And so with that, I hope to kind of go through everything that it's in the README. If you please notice some errors, let me know. But I think with that, I kind of covered everything that I wanted to talk about. Again, there's going to be another workshop for more advanced. It's going to be hands-on, completely, totally like working in the terminal and like running with your own data. And there's going to be another one in Spanish for those that you are interested in. But yeah, with that, I really want to thank every one of you for joining us today. And I am so happy for you. Yeah, I'm really happy to kind of give this workshop. And yeah, with that, I'm happy to take any questions.